Okay, good afternoon, everybody. It's my pleasure to be able to talk to all of you. I hope you find this useful for your purposes. A couple of things I want to say up front. There'll be a disclaimer in the first real slide, and please pay attention to that. The other thing is I'm going to be talking very quickly and going through slides very quickly. That's not just because I'm a New Yorker. It's because there's a lot of stuff to talk about. There's a lot of information I had to leave out anyway, because this is such a completely interdisciplinary topic. What I want to say is that the presentation will be available to you both in recorded form and as in the form of Keynote and PowerPoint slides that you can download for your own use. So to repeat that, some of the slides have a lot of stuff on them. I'm going to go through them relatively quickly. You will be able to download them, look at them, use them at your leisure. Okay. Please, very important, note the following disclaimers. This is not a source of medical information about coronavirus. Don't think about it that way. I will be providing links to what are the proper sources for medical information. And if at any point in time down the road, anything I say or have in this presentation conflicts with CDC or NIH advice now or in the future, please trust those primary sources and not this presentation. The other thing is this situation is changing minute by minute. So some of this information will probably already be outdated by the time it gets posted. It's very rapidly changing. So this should be viewed as a sort of an informational time capsule as of today. And the way that the presentation is structured, because there's so little we actually know about this new disease, and that information is changing, I'm going to be putting it into historical and medical context with other infectious diseases and epidemics of the past, and review some of the lessons that we have learned, or at least lessons we should have learned from past epidemics and pandemics. So please use this information to inform your teaching and to inform your students and other people of scientific facts as we currently understand them. Please use this information to combat misinformation and intentional and, in my opinion, criminal disinformation that is being distributed for partisan political purposes. This is a life and death medical struggle globally. There's no room for politics here. And this is one thing that all of us as science educators can do to help our communities and society by expanding the presentation of accurate, scientifically informed data and scientific perspective. Because when the misinformation and the disinformation gets out there, this kind of thing happens. It is incredible to me that one of the most important people in this whole informational process is now receiving personal threats from conspiracy theorists because he dares to disagree with a certain individual. The other thing is this map shows places where people are stopping their travel according to responses to the epidemic. The areas where people are stopping travel are in gray. Areas that are in various shades of that reddish brown are not stopping their travel. They're still traveling. They're still gathering in groups. And I won't make any kind of comment about the geographical distribution, just to show you that there are significant parts of the country that are not yet taking this seriously. So wherever you are in the country, get some of this information out there. This is I can't say this often enough, an emerging, rapidly evolving situation. The most important places for you to get any medical information are from the CDC website, which has a special homepage for coronavirus, and NIH, which has its own page for coronavirus. All right, this is what the CDC homepage looked like as of this morning. You can see it's got very important links on it. This is what the NIH homepage looked like this morning with all of its links present. Another place, if any of you read Science magazine, is they have a special coronavirus research commentary and news section, which is being offered outside of their usual paywall, so any of you can access it for your own purposes. Okay, now, although we don't think of it a lot in the present because we thought we had infectious diseases licked until AIDS came along, diseases have always been really major drivers of human history. Some of them give examples of how powerful pathogens can be, and others offer lessons of ways to combat them if we pay attention to those lessons. The stories of these past epidemics aren't widely known, which is why I'm covering them today, and they do offer important context for what's going on now. And again, our current post-factual world makes understanding disease especially essential. Students have to learn how to separate fact from fantasy, spin, conspiracy theories, and frankly, outright lies. And I'll just leave that right there. So, to understand coronavirus and other infectious diseases, we have to consider scientific information in three main areas. What's the pathogen like? What is the kind of creature or virus that is causing a particular disease? How do individual hosts' immune systems respond to this pathogen? And then what do the populations of the hosts look like and how do they behave? Okay, so the first thing is we are now getting excellent visualizations of coronavirus. Like many viruses, this is not an organism. When people say that the virus can live on a surface, viruses are not alive. They're inert packages of genetic information enclosed in a protective coat with secret keys to get in and out of their host cells. They're not really alive. But these organisms have spike glycoproteins, those big yellowish green things. They have hemagglutinin esterase protrusions from the outer membrane. They have the envelope, which surrounds the genetic material in the center. It is this envelope that contains lipids, among other things, and is susceptible to being torn apart by soap, which is why washing your hands is a good idea. This pink spring-looking thing inside is meant to represent the virus's RNA, because it's an RNA virus, not a DNA virus, surrounded by protective proteins. So that's what it looks like. The characteristics of pathogens that are particularly important, the two most important ones, are transmissibility. How easily is a pathogen transmitted from one host to another, and when, during the course of infection, can that transfer occur? We now know that coronavirus can be transmitted before the host shows any symptoms at all, which is one of the reasons it's been spreading so quickly. The next important characteristic is virulence. How severe is the disease caused by a pathogen? How much damage does it do to the host? And we're getting more and more information about that, about coronavirus on a daily basis. Just for a minute up here up front, looking at those two parameters, the area enclosed in pink on this graph shows where the coronavirus probably falls. These are kind of like error bars the size of that rectangle. The x-axis shows the average number of people infected by each sick person. So that's an axis that shows how transmissible the virus is. And the y-axis shows the percent fatality of this particular virus. Notice we have some familiar ones plotted on here. This is Middle East respiratory syndrome, bird flu, Ebola, smallpox, Spanish flu, SARS, measles, chickenpox, polio, the common cold, etc. So you can see that this virus is more transmissible than most of the other coronaviruses which have come around, which are like MERS and bird and so on, and SARS. And it is, there's some significant range of lethality depending on the health and age of the host's immune response, and so on and so forth. So it is more, it has a higher degree of virulence than the seasonal flu or the common cold or chickenpox or measles, but less than some other diseases. It's not as deadly as smallpox, for example. Okay. The third thing is is called immunogenicity. How rapidly can a pathogen be recognized by the human immune system? And that's actually of course, a joint characteristic, both what does the parasite present and what does the host immune system recognize. Also, there's genetic variability. How often and how much does a pathogen change genetically? In other words, how rapidly does this particular pathogen evolve? Now, one thing that I have to do is I have to introduce a word which many of you have probably heard, but you may not have. The word is zoonosis. And you may not believe it, but as a textbook author, I despise key terms. I really view the list of key terms at the end of every chapter as a wave of tidal nonsense that can overwhelm the important content. So if I introduce you to a new term, it's important. Zoonosis is important because a zoonosis is any disease that can be transmitted from one host species to another and sometimes back and forth. All right? This, for example, is a schematic representation of the influenza zoonosis. All of these organisms, and that's my son about 20 some odd years ago in the lower right-hand corner, but the influenza zoonosis includes wild birds, domestic poultry, pigs, humans, and sort of peripherally horses and even marine mammals. And we'll come back to this later, but this is just to give you an idea of what a zoonosis is. All of these organisms can be infected by influenza, and to varying degrees, they can transmit this infection to other organisms. Now, there are a whole bunch of other headline-grabbing zoonotic diseases that have appeared on the horizon over the last 20, 30 years. This whole list, every organism, every disease that is on this list does in fact participate in a zoonosis. And I'm not going to go through and describe them. You can come back and look at them and figure out what you can find out about each of their zoonoses, right? Next thing we need to look at is the immune response of individual hosts, okay? So the ability to recognize a pathogen, speed in mounting an immune response, history and memory of the immune system. And so both the ability to recognize the pathogen and the speed with which the immune system can mount a response depend very strongly on whether or not the host's immune system has ever encountered this pathogen before, right? If a host's immune system has encountered a pathogen or a pathogen that is similar in terms of its external characteristics to this one, it can usually mount a rapid response. If, however, the host's immune system has not encountered a pathogen before, it takes longer to recognize the invader and longer to mount a response. And this delay in response lets the pathogen go haywire inside the host and can result in fatal disease. Okay. The immune system, as those of you who are teachers and have tried to teach about it know, is fiendishly complex. So I'm only going to discuss a very small part of that today. The fact that the immune system recognizes pathogens by recognizing and responding to antigens. And antigens are any substance on the outside of a pathogen, the outside of the viral coat or the outside of a bacterial membrane, as the case may be, that human antibodies can recognize. And when a human immune system comes into contact with an antibody that it has encountered before, the antigen and antibody bind to each other, and that prevents the virus from binding to the receptors on the cell that let it get inside. If, however, a new viral antigen comes along and the old human antibodies have never seen it before, it can't form that antigen-antibody complex, and the body essentially scrambles to try and create new antibodies at random almost to try and essentially rapidly evolve a matching antibody to these new antigens. Okay. Then we have the nature and behavior of host populations. How big is the host population? How dense is the host population? How mobile are individuals within and between host populations? And then the percent of the population altogether that has educated immune systems. In other words, how much of the population has encountered this pathogen before. It's a fascinating topic, and I can't go into it here. I just wanted to make you aware of the fact that there is, in fact, a discipline that studies the way that human interactions with each other, with other societies, and with the environment and animals in the environment affects the spread of disease. And this is called human social ecology. This is an excellent book. It is a professional book, not a trade book, but you can see just from the photos that have been chosen for the front cover of the book, here we have airplane travel, which gets us all lots of places, which is great, unless we're carrying pathogens. And down below, you have a situation in a less developed country where you can sometimes have sewage running in the street, and it can spread diseases that way. So human social ecology includes all of the things we've talked about in terms of population, where and how people live, the way we travel, and the way we produce our food. So changes in these factors change the interactions among all the members of those zoonoses. And those interactions affect how the pathogens evolve. They affect how they get transmitted among individuals and species within the zoonosis, and how they make us sick. This is incredibly complicated, and it requires carefully planned, scientifically informed, and scientifically directed public health measures. And this is one of those images that I'm going to say you should come back to later and look at, but it shows just the most important of the interactions that occur around zoonoses. You have here wildlife emerging infectious disease. That's what EID means. We have human emerging infectious disease, and we have domestic animal emerging infectious disease. You have some diseases that involve only domestic animals and humans, some that involve only wildlife and humans, some that involve all three. And you can see all the different characteristics of human social ecology that affect the amount of disease that's present in those different areas. Okay, now historical examples can show us how these kinds of things play out in the real world. There are two excellent books. The first is a Pulitzer Prize-winning book by Jared Diamond called Guns, Germs, and Steel. By now, this book is old enough that some of its information has been updated and superseded, but it's a wonderfully good read, and if you choose the stories carefully, you can get a lot of information for your students. 1491 is meant to be a story about the Americas and indigenous Americans before the arrival of Europeans. And to give you an idea, only in the last 10 to 20 years have we become aware of the fact that by the time Europeans were actively colonizing North America, diseases that had been previously introduced to the Americas from Europe and elsewhere had killed off somewhere between 90 and 95% of all indigenous Americans. Think about that a minute. 95% of the indigenous population was killed not by armies, not by smaller conflicts, but by disease. And in fact, the cover of Guns, Germs, and Steel shows a sort of apocryphal painting of Pizarro and the Inca during the Spanish conquest of Peru. So, background here for this. Why did that happen? Well, humans in the old world were pretty much connected by the time the age of exploration came around. Europe, Africa, the Middle East, and Asia had been in contact and had been trading diseases for centuries. Nearly everybody had been exposed to several diseases very early in life, and those who did survive had educated immune systems and were therefore largely immune to those diseases, which were still hanging around. To give you an idea of how bad smallpox was, in Europe, for a significant length of time, people would not actually name their children until they survived smallpox. So think about that for a minute. On the other hand, humans who were indigenous to the Americas had been completely isolated from those populations and from all those diseases. Their immune systems had therefore never seen those diseases. The immune systems were completely naive, and that's why they were so hard hit by these introduced diseases, because they were serious diseases and their immune systems had no recognition of them. All right, let's consider the Aztecs, for example. The Aztecs were a great civilization. in Mexico. This is a artful reproduction of the Aztec capital city, which was built on an island in a lake that could only be approached by causeways. And this was what Cortez and his men went in to conquer. Now, what's the standard story here? Oh, Cortez was a brilliant tactician. The Aztecs had legends about bearded guys in boats, and Cortez made alliances with Aztec rivals. And somehow those factors combined let 500 to 600 soldiers, 100 sailors, 16 horses, and a bunch of guns defeat an Aztec army that numbered somewhere between 200 and 400,000, not including their support personnel. Is there anything wrong with that story? There's something wrong with this picture, which shows many more horses and many more Spaniards attacking the capital city than actually existed. So what is wrong? Did Cortez have a secret weapon? He didn't even know he had a secret weapon. That secret weapon was smallpox that the Spaniards brought with them, that they introduced to the Aztecs. And by the time several weeks into this first contact, the Spaniards had to fight their way out of the capital city in a battle called La Noche Trista. Half of the Aztec population of the capital was already dying of smallpox. So why don't we need to worry about smallpox today? Because of vaccination. And just a quickie to show you, this is an artist's example. People did not really take very well in Europe to the introduction of cow pus to the skin of people. And this guy sort of fancifully envisioned cows erupting from people's bodies. So anti-vaxxing isn't new, but this was a long time ago, and we should have learned better by now. Now we'll move on to the Great Plague of 1665 in London. London had had more than 35 plague outbreaks by that time. This particular plague was caused by a bacteria that was part of a zoonosis that included rats and fleas. It killed roughly 15% of the city's population. There were no antibiotics or other useful drugs, but the British actually figured out how to limit the spread of this disease by a combination of strictly enforced quarantine and social distancing. Okay, and after they implemented those policies, Britain did not experience another plague outbreak of this scale again until today. So one of my favorite images of how bad the plague was, this is from an Ingmar Bergman film called The Seventh Seal, and it shows a Swedish knight playing chess with death. I won't tell you who won this particular game. But what was going on here? We had, this is a page from the UK National Archives. The link is up top. It's an excellent educational resource talking about the plague of 1665. And the question is, what did London do? They actually did some social distancing, all right? And what did that look like in 1666? Well, the doctors went around wearing these masks that some of you may have seen before. What they would do is they would stuff the beak of that mask with fragrant herbs because they thought that the herbs would filter out the bad air that they thought was the cause of the disease. But the king didn't want to depend just on that. He put out these orders, which are long and detailed and written in a not particularly legible script. But what that website has done is it's retyped them in a legible script, written them all out, and then for you teachers, it has provided a whole bunch of questions to ask your students. How do orders 6, 7, and 8 aim to prevent it? How long were infected houses shut up for? So this might inform some discussions about the importance of quarantines and social distancing. Then we move up to the influenza pandemic of 1918, which was one of the worst, the worst epidemic the United States had ever known until the present day. And it was, in fact, a ghastly experience for the entire world. This 1918 pandemic, also dubbed the Spanish flu, killed 675,000 Americans, and somewhere between 20 and 50 million people around the world. And to put that in perspective, that's more than all the wars of the 20th century put together. World War I, World War II, including the Holocaust, Korean War, all of that stuff. This plague, this Spanish flu, killed more people than all those wars. Armories and other places were transferred into massive hospitals with cots for the ill. Of course, they didn't have antibiotics or any, and certainly no antiviral medications. There wasn't much they could do. This particular scene was in the armory at Fort Devens, which is a few miles from where I live in Massachusetts. There were signs posted all over the place as the influenza started and spread here in the United States. Often it was complicated with bacterial pneumonia. These are instructions, basically go home and go to bed, stay home, and they closed theaters, they closed public places. They discovered again in 1918 that social distancing in fact works. And some of you may have already seen this. There are very interesting data from several American cities, excuse me, including Philadelphia, New York, and St. Louis. Philadelphia waited 8 days after their death rate began to take off because there was a big wartime-related parade scheduled. All of the officials in the medical profession in Philadelphia said, don't do this, cancel the parade, have everybody stay home. But the chief medical officer, who was a political party apparatchik, was worried about repercussions politically if he canceled the parade. So he said, no, we're going to go do it anyway. And as a result, 2 or 3 days after the parade happened, cases really started to take off. And by then, when they finally did the sort of stay-at-home orders, it was out of control, and they had the highest rate of disease and the highest death rate of all the cities that we have data for. St. Louis, on the other extreme, said, uh-oh, as soon as cases started showing up. And they immediately introduced social distancing measures. As a result, they flattened the curve. They had a lot fewer people die in total. But as you see in this graph, they relaxed the quarantine too soon, and the disease rebounded, and they had a recurrence of cases. Still, with the first peak and the second peak together, they had a little bit more than half as many deaths as Philadelphia did for ignoring that. We learned this 350 years ago, and the cities that took note benefited. New York was very good. It instituted the quarantine very early, kept it for a long time, then released it. And by the time New York released it, there was only a slight secondary bounce. So they had the lowest death rate on the eastern seaboard. Okay. Now here is an interesting simulation of the difference between transmission when people can move around and gather in groups and do whatever they want, or when they're told to stay at home and distance. And what you'll see is the little dots here will start moving around, and they are either colored blue, which means they're immunologically naive, brown, which means the individuals are sick, purple, which means the individual has recovered. And we'll be comparing the free-for-all, which is shown on the left-hand side of that group above, and the extensive distancing, which is shown on the right. And I'm including this simulation here, courtesy of the very generous Washington Post, which okayed its use for this purpose. I'm going to run it now and watch what happens. So you see here people getting infected. On the left, very quickly, spreading very quickly. On the right, more slowly, fewer people being infected, and people having a chance to recover before other people got sick. These are the two curves that are produced. Obviously, it's the curve on the right-hand side that we would like to duplicate, because we would really like to make sure that we don't overwhelm our healthcare facilities, and that's already happening. In terms of modern disease prevention, though, smallpox and measles and polio are actually best case scenarios, because those viruses do not undergo much genetic change over time. In other words, they don't evolve, or they evolve very slowly. So the smallpox vaccination that I got as a child is still pretty good at protecting me today. I won't tell you exactly how many years later. Whereas you know that influenza, on the other hand, you got to get a flu shot every year, and even then it doesn't always work. So this is the point. Many bacteria and viruses do evolve, and that's why understanding evolution matters to medicine and biomedical research. And in fact, Dr. Stuart Levy, the author of a wonderful book called The Antibiotic Paradox, he was one of the first physicians, as opposed to clinical researchers, who tried to ring the bell and tell people about the danger of antibiotic overuse and the evolution of antibiotic-resistant bacteria. And this is one of his statements: medicine and public health would be much better off if medical students were taught as much about Darwin as they are about Pasteur. And that's something to ponder. So let's go now and look at how influenza works and why it's such a pain in the neck, and then we will compare it to coronavirus. So how do they make us sick, first of all? Again, I will move through this with lightning speed. You can download the presentation and use these visuals and work through them on your own. One of the spikes of the on the outside of the flu virus particle is called hemagglutinin. And hemagglutinin binds to a receptor that exists on the surface of host cells, and that's a sort of secret key that opens the lock and lets the virus get its genetic material, RNA in the case of influenza, into the host cell. Once that material is introduced, it is put into action. It hijacks the machinery of the cell to produce new viral genetic material and new viral proteins, puts them together and helps them get out of the cell. And another one of the surface proteins on the virus is responsible for helping the virus bud out of the host membrane and move on to infect other individuals. So here's a schematic representation of the influenza virus. Notice that in some ways it's similar to the coronavirus, and in some ways it's different. The one set of spikes on the outside are called hemagglutinin. And hemagglutinin, again, binds to receptors on the host cell surfaces and tricks the cells into taking the virus inside. The other compounds that are sticking out on the surface of the cell are called neuraminidase. And neuraminidase helps the newly formed virus particles get out of the cell. And the genetic material of the influenza virus is 10 genes that are carried on 8 separate strands of RNA. Remember that, 8 separate strands, because that's significant, as you'll see in a few minutes. So these viruses are locked into an evolutionary arms race with our immune systems. These surface proteins, H and N, act as antigens to trigger our immune response. So for that reason, viruses are under intense pressure for natural selection to evolve new forms of H and N that our immune systems can't recognize, even if we've had the flu before, okay? The most common known forms of hemagglutinin, there are 16 of them, and neuraminidase, there are 9 of them, are given numbers. So H1 to H16, N1 to N9, and these numbers are used to name specific flu strains. The 2009 swine flu was scientifically called H1N1. The 2011 bird flu was H5N1. The 2013 bird flu was H7N9. Okay. Now, the big question: why are some flu strains nuisances while others can cause serious or lethal illness and really threaten a much larger population? Remember transmissibility and virulence. Now add immunogenicity. How rapidly can a viral strain be recognized by human immune systems? Those nuisance strains, the little, discomfort, body aches, coughing, maybe you stay home for a day or two kind of strains, are the result of minor mutations in flu genes that produce small changes in viral antigens. This is called antigenic drift, and these kinds of mutants cause those annoying run-of-the-mill kinds of typical winter flus, but they're not usually life-threatening. On the other hand, sometimes you get major genetic changes that produce major changes in antigens. These are called antigenic shifts, and they can produce lethal strains that cause global epidemics, which are also called pandemics, like the pandemic of 1918. So what happened to influenza viruses in 1918. Can it happen again? And the answer is to look again at the influenza zoonosis. Okay. Now, if you look at the arrows that indicate transmission here, the solid arrows indicate transmission that occurs easily and often. So domestic birds give people the flu very regularly. Swine and people can trade viruses back and forth very easily. The dotted lines here mean that transmission from one part of the zoonosis to another is very rare. It only occurs now and then. Now, what does that mean? The influenza strains that are in these different parts of the zoonosis are reproductively isolated from each other in different hosts. And that means that different strains can evolve different kinds of genetic variation in these different parts of the zoonosis. And the variation can be troublesome for us. For example, here's a distribution of influenza A hemagglutinin subtypes in people, some other mammals, and aquatic birds. So we have H1, H2, H3. H5 is kind of sometimes present. H9 is sort of sometimes present. Other mammals typically get those as well, although other mammals sometimes have more H7 than humans do. Look at all the different subtypes in aquatic birds. And at least half of these have never been seen by a human immune system anywhere. And by now, you should get an idea of why this is dangerous, okay? But how do the strains that are only found in ducks get into people? They get here by something called viral sex, okay, which of course students would love. You know, you talk about viral sex and you know you've got their attention right away. What happens? You get two different strains of influenza. I've only done 3 strands of RNA here because I'm not technically sophisticated enough to do all 9. But you get 2 different strains infecting the same host cell at the same time. They both inject their genetic material into the cell. All of it is replicated. And then those new viral particles, as they're being assembled to bud out, do a kind of 1 from column A, 2 from column B sort of thing. And the original viral genetic fragments can get recombined in different combinations than either of the original parent strains. Right? And as a result, you can get some recombinant viruses that carry either new genes or new gene combinations that are great for the virus and not so good for us. And that's what happened in the really dangerous H5N1 that luckily we were able to snuff out. There was one strain, H9N2 in quail, a strain H5N1 in geese, a strain H6N1 in teal. Those all had viral sex inside an infected quail, which then transmitted that virus to chickens, which then transmitted it to humans. And the death rate of humans who were infected by that virus was about 33%. Happily, it was not easily transmissible, so they were able to snuff out that epidemic before it got very widespread. The strains of bird flu that we know about so far are virulent. They can cause serious illness and death, but they're not transmitted from person to person easily. I don't have time to explain why, but we do have an idea about why that's the case. Strains of swine and H1N1 that we know about have low virulence. In other words, they don't cause serious illness that often, but they are very easily transmitted among people. So combine viral sex with strains that have evolved in different parts of the zoonosis, and we could be in trouble. And these are just some of the ways that that can happen. A pig can become infected with both avian and human flu. They have viral sex, and that becomes a pandemic strain. A human who's already sick with flu catches avian flus, a little viral hanky-panky goes on in that person, and you get a pandemic strain. Or you can much less often get a mutation or accumulation of mutations that can give you a nasty pandemic strain. And again, I won't go through this in detail, but you can download it and look at it yourself. This is a historical recreation of what happened in the influenza strains that produced the 1918 influenza pandemic. And then as a summary, these are the most important factors in determining how seriously a virus affects humans. How much of a pandemic threat does a particular virus present? You have factors of the virus itself, you have factors of the host, and here they've grouped what I called host population factors into external factors, which also include coexisting conditions. You know, does the person have tuberculosis or asthma? Is there secondary bacterial pneumonia? Do they have HIV? All of these factors combine to determine how bad this is going to be. Now we go to coronavirus. And again, it's emerging, rapidly evolving. Everything I say here may be out of date tomorrow. I doubt it, but some of it will be, and a lot of it will be superseded down the line. So keep going to these links that I'm giving you to keep updating your information. This again is the structure of the coronavirus. You can see the similarities and differences between coronaviruses and influenza viruses. They do have both neuraminidase and hemagglutinin showing on the outside. And again, what we have here is virulence and transmissibility. This same graph that I showed you before, we'll look at again. And so the transmissibility of this particular strain of of coronavirus is right in here, about the same, a little bit less than polio, a little more than seasonal flu, more than some of these others, but much less transmissible than measles. Okay, and again, the fatality rate runs a gamut here, depending again on age and those other factors of the host. Not as bad as SARS or Spanish flu or MERS, but significantly worse than measles or polio or the seasonal flu or the common cold. Now, the coronavirus, it is turning out, and again, this is an evolving, developing situation, has high rates of evolution. It mutates and changes regularly. The effect of that rapid rate of evolution on potential vaccines is as yet unclear, because we don't really know which aspects of the virus those mutations affect. Okay, so right now, and this is another excellent source of information for you, a website called MedPage Today. And so far, and again, this is as of a few days ago, they're saying, well, there are a bunch of different strains of this virus, but so far, they seem to be affecting things that don't make it more difficult for us to make a vaccine. Let's hope that stays the case, and we'll see what happens in the future. You've heard about pangolins. What's the story with pangolins? Well, you probably also heard that coronaviruses are most often found in bats. And people and bats in different places don't come into an awful lot of direct contact, but one genetic reconstruction of the history of the coronavirus that's now in people suggests that there may have been either co-infection of a pangolin with a couple of different coronavirus strains, or that a mutated form of coronavirus was transferred from bats to pangolins, then it mutated some more within the pangolins and was transferred to humans through illegal wildlife trade, because this is an endangered species and you're not supposed to be trapping and eating them. But so that's one place where conservation biology comes into contact with epidemiology. The more of these native species and the more different kinds of species that are involved in close contact with humans, the more likely this kind of transmission could be. Now, I want to say right here, this is a hypothesis right now. We don't know exactly what happened. We're not 100% sure that the pangolins gave the virus to humans, but that's the current hypothesis based on data to date. This will undoubtedly change, either be reified and confirmed or superseded and replaced as more information become available. If you want to follow these kinds of data, here's another excellent website for you to use. It's called nextstrain.org, which does real-time tracking of pathogen evolution. They have fantastic stuff on here, which I don't have time to show you, but this is their current homepage focusing on the coronavirus, and it has the latest data and analysis that they keep updating on a regular basis. Again, another place, if you want to track what's going on with coronavirus in terms of epidemiology, is this website of the Johns Hopkins University School of Medicine, their Coronavirus Resource Center. I took this screenshot this morning. So 100,000 confirmed cases, 50,000 plus deaths, and about 200,000 recovered. So that means the rest of them are still sick. And you can look at it in an interactive map. You can explore the growth of new cases worldwide and do other things. Here is an example of that map, again, as of today. So this shows where the centers are. You can zoom in, you can watch over time, you can go back in time. And this shows that as far as total global cases are concerned, this pandemic is still in the exponential growth phases. Now, again, I'm not giving you any information on what to do about protecting yourself. You go to the CDC pages and get that information yourself. I've given you the link to the updated page there. One reason that I'm not talking about this is because if you recall, originally they said that most of us should not be wearing masks and that medical providers should be, or individuals who are already sick should wear masks, but not ones that are not. That recommendation changed just this week. Now they say that if you're going outside, everybody should wear some kind of mask. And the details of what those masks need to do, some of them can be very simple and homemade. All of those are provided here and on a couple of similar parallel pages. The blog of the director of the NIH is talking here about social distancing. So if anybody in your circle doesn't understand why social distancing is important, you can send them to this page and hear Francis Collins discuss it directly. Brilliant man and a very incredibly important source of information. They also, for those of you who are more molecularly inclined, publish information about the structural biology and the way what they're learning about the structure of the virus relates to efforts to develop a vaccine. Another a page here on MedPage Today talks about what's going on with all of the protective equipment for medical people, and again, that threat to Dr. Fauci. These pages are updated every day, and you can subscribe to an email server that will ding you 2 or 3 times a day because the information is changing that quickly. And they also are very good about debunking misinformation and lies. And one of the problems that they had at the beginning was it was originally thought that people my age were in more danger of lethal disease than people in their 20s, 30s, and 40s. It turns out now that that's not the case. People my age are in trouble because our immune systems aren't good enough. People in their 20s, their immune systems are cranking so hard that sometimes it's overreaction by the immune system, what's called a cytokine storm, that attacks the tissue of the lung that's already infected and causes additional damage in addition to what the virus is doing. So this is why you have to keep up to date on information, and don't ever take information from the web whose original source you cannot document. You must be absolutely certain that it comes from one of the reliable sources that I've been showing you here. And then for those of us who still do need to have contact with the public, this is advice for medical providers on what do you do and how do you protect yourself, and how do you even deal with the emotional fallout from knowing that you're stepping on landmines every time you leave your house and walk into your hospital. Okay, if you would like to participate, or if you'd like your students to participate in an interactive online experience, this is a website that's been set up by Boston Children's Hospital, Harvard Medical School, and a friend of mine who used to work for AAAS is involved in this. It's, you sign up, you tell them how you are, you tell them what's going on around you, and they end up using those data to create a map that's separate from information about testing and hospital admissions, and is a much more live and directly changing focus on how the epidemic is spreading. Okay, so as science educators, everybody should really take our abilities and social responsibility and our dedication to science education seriously, and teach about the science not the politics of infectious disease as if our lives depend on it, because as a matter of fact, they do.